Hi everyone. So in yesterday's video, toward the end, we did some examples where we were kind of translating back and forth between polar equations and rectangular equations. So in today's video, we're going to focus on how to graph polar equations. And this isn't something we're going to get like super deeply into. We're just going to do kind of a few examples, and then I'm going to show you some other ones on Desmos. So what do I mean when I say a graph of a polar equation? Or, even more generally, what do I mean when I say a polar equation? Well, what we're used to graphing are equations that relate x and y, right? So we're used to graphing equations that relate, or that give a relationship between x and y. So an example of an equation that relates x and y would be something like, y is equal to x squared. And so when you go and graph that equation, you might just kind of know off the top of your head what that graph looks like, right? It's a parabola, but how would you get the actual points on that parabola? Well, you would be kind of looking for points that satisfy this equation. So for example, the point 2, 4 would lie on this graph, because if you plug in 2 for x and 4 for y, then that gives you 4 is equal to 4. So basically the main idea I'm trying to kind of just remind you of here is that for any equation, when you're graphing it, the graph is always going to be all of the points that satisfy the equation. And so the way that we're going to go about graphing our polar graphs is we're just going to make tables. We're basically going to make tables of r and theta and use that to make our graph. So an example of a polar equation might be something like this. So in yesterday's video, we did an example that was r is equal to 4 times cosine of theta. So we'll come back to this example a little bit later, but I just wanted to kind of throw it out here as like a first example. So let me just write down some context here. So today we will be graphing equations that relate r and theta. So how will we go about graphing this? Well, we'll basically make a table where we're going to choose different values of theta, the same way that if you were graphing this equation, you would make a table where you would list different values of x and see what you'd get for y. For this one, we're going to list different values of theta and see what we get for r, and then graph them the way that we've been graphing polar points in the past couple of videos. So before we get into that, I want to look at a slightly simpler type of polar equation that we can graph. So when we're talking about rectangular coordinates, there are some examples of rectangular equations that only have one variable in them, right? So sometimes rectangular equations don't contain both x and y. And that's fine. That doesn't mean anything about whether you can graph them or not. So examples of that would be something like x is equal to 5. So what does that look like? That would be a vertical line at an x value of 5. I mean, I almost just want to say at x is equal to 5, but I'll say at an x value of 5. So why would that graph look like a vertical line? Well, let's think about what this equation actually means. If you have the equation x is equal to 5, basically that means that there's no information about y. Y can be anything. But no matter what y is, x is always 5. And so what does that look like when you graph it? Well, if x is always equal to 5, that means that you want to go to an x value of 5 and make a vertical line, because basically this vertical line is a statement that no matter what you plug in, or no matter what y value you're looking at, x is always 5. And then similarly, if you had an equation that was like y is equal to 2 or something like that, that would be a horizontal line. And that would be saying it doesn't matter what x is, y is always 2. So similarly, we can have polar equations that don't contain both r and theta. And so that's what we're going to start with. And those are kind of the simplest ones to graph. So let me just kind of say that here. So similarly, polar equations don't need to contain both r and theta. And so similarly to how when you're graphing something like x is equal to 5, it doesn't really make sense to make a table, right? There's not really much that you would put on the table. It's more like you're just like, okay, x is always 5. Let me think about what that looks like. And so similarly, when we graph these next two polar equations, we're not really going to make a table, or we're not going to make a table, because I think it makes more sense to just kind of think about what are the points on this space that satisfy the equation. So one example of such an equation would be something like r is equal to 3. And maybe I'll say graph r is equal to 3. So let's think about what that means. If r is equal to 3, that means that no matter what the angle is, theta can be any angle, but the radius is always 3. R is always 3. So what is that going to look like? Well, it's going to look like a circle with a radius of 3, right? Because it's basically saying no matter what angle we go to. So if you wanted to, you could make a table, right? You could say, okay, when the angle is pi over 6, r is 3. And so that would give you a point here. When the angle is pi over 4, r is 3. That would give you a point here. When the angle is pi over 3, r is 3. That gives you a point here, and so on. So no matter what angle you're at, you always get r is equal to 3. So I want to quickly show you, you don't need to do this in order to graph it, but I think it's a kind of a nice connection to make. We could also translate this into rectangular coordinates. So you can also translate to rectangular coordinates. I'm not saying that this is how you should do it. I think I would really like if you could just kind of recognize the fact that if r is equal to 3, the fact that that looks like a circle, but it's more like I just want to kind of show you what it would be in rectangular coordinates, because it's kind of cool to see that it agrees with what we have drawn here. So how would you translate this into rectangular coordinates? Well, we know that r, so in yesterday's video, we talked about how r is equal to plus or minus square root of x squared plus y squared. Right, so I'll write that down here. R is equal to plus or minus square root of x squared plus y squared. And then we also had a couple of other facts, right? We knew that, that r times cosine of theta is equal to x, and r times sine of theta is equal to y. But this is really the only fact we're going to be using here. So when we have this equation, r is equal to 3, we can instead write it as plus or minus square root of x squared plus y squared is equal to 3. And then we can square both sides. And so when we square both sides, this plus or minus goes away, because when you square something, it doesn't matter whether it's positive or negative. And so we end up with x squared plus y squared is equal to 3 squared, which is 9. And so if you remember from pre-calculus, what this graph looks like, x squared plus y squared equals 9 is a circle centered at 0, 0 with a radius of 3. And that's exactly the picture we drew. So I think that's kind of a nice thing to see, because I think it just kind of, maybe it helps you see why this is true, right? Why like r is equal to plus or minus square root of x squared plus y squared, that there's this kind of connection between basically circles and translating between polar and rectangular coordinates. Okay, so let's do another example. So we just did an example where it was just r, and now we're going to do an example where it's just theta. So we're going to graph theta is equal to pi over 3. So what is this telling us? This is telling us that it doesn't matter what the radius is. It doesn't matter what r is. R can be anything, but the angle is always going to be pi over 3. And so that means that we're going to have a line at an angle of pi over 3, and it's going to go in both directions, because you could have, for example, pi over 3 with an r value of 1, and that would give you a point here. You could have an angle of pi over 3 with an r value of 2, that would give you a point here. But you could also have the angle of pi over 3 with an r value of -1, and that would give you this point. Or pi over 3 with an r value of -2, and that would give you this point. So, I'm drawing this line going both ways, but really the angle pi over 3 is pointing in this way, this direction. It's just that because there's nothing said about r being positive or negative, that tells us that if we're to graph all of the points that kind of fit with this equation, they'll include points both in the positive and negative direction. So they'll give us a line. So I'm sure you could also translate this into rectangular coordinates, but I think I wanted to do it on this previous one just because I thought it was kind of a nice connection. That's not really the way we're going to be doing the rest of these. So for the rest of the things we're graphing in this video, we're just going to be keeping them in polar coordinates. Okay, so we're going to do another example, and now this is going to get a little bit more involved. So this is now going to be an example where we have to make a table, as you can see. So it's going to have both r and theta in it. So the first example I actually want to do is the same as an example that we worked with yesterday. So yesterday, one of the equations that we translated from polar to rectangular coordinates was r is equal to 4 times cosine of theta. And so if you remember what that ended up being in rectangular coordinates, I'll kind of write it off to the side here, but we're not going to be using that to help us graph it. It's more just to kind of compare. So remember from last time, we translated this into rectangular coordinates, and we got, I believe it was x minus 2 squared plus y squared is equal to 4, I think. We'll find out whether that's right soon enough. But that's something we did in yesterday's video. So we should expect it basically to be a circle, but I really want you to see kind of how that circle comes out, not from the rectangular coordinate point of view, but from our points. Okay, so basically what we're going to do is we're going to plug in different angles. And actually, I'm going to color code this a little bit. It's not so important on this example, but I think it might help on the next example we do. So I'll do it here as well. So we're basically just plugging in the different angles and seeing what we get for r. So for example, if we plug in 0 for theta, we get r is equal to 4 times cosine of 0. Cosine of 0 is 1, so we have 4 times 1, which is 4. And I won't like speak through all of these. Some of them I'll just write down. But for example, let's say we wanted to do pi over 6. So we know that cosine of pi over 6 is square root of 3 over 2. So then we would have 4 times square root of 3 over 2, which would give us 2 times square root of 3. And that's approximately equal to 3.46. And I'm just going to fill the rest of these out because I don't think it's super interesting for you to just watch me do this. But I would encourage you to pause the video and try to do these yourself. Try to plug in these different angles. You're basically just plugging in the angles into cosine of theta and then multiplying that result by 4. And that tells you what r is equal to. So I'm just going to fill the rest of this out. We should get 2, 0, -2, -2 root 2, -2 root 3, and -4. And so -2 root 2 is approximately -2.83, and -2 root 3 is approximately -3.46. Okay, so once we have all of these, this table filled out, how do we actually plot these points? Well, it's basically exactly the way that we were plotting points in Monday's video, or maybe it was Tuesday. Tuesday, Wednesday. I'm losing track. I think it was Wednesday's video. Whatever was the video where we were just plotting points in polar coordinates. So for example, if we wanted to plot this point, 0, 4, that means we go to an angle of 0. And so what does an angle of 0 look like? It is just, flat here. And then we go to an R value of 4. And so that means that our graph is going to have a point here. And then next up, we go to pi over 6, comma, 2 square root of 3. And so that means we're going to an angle of pi over 6, and we want our radius to be approximately 3.46. So I'm just going to kind of estimate. So here is 3, here is 4. So it's somewhere in between, just about halfway, a little less. So maybe somewhere like that. And then we go to an angle of pi over 4. And that is going to give us 2.83 approximately. So if I go to this angle of pi over 4, and then 2.83 is going to be something kind of like, maybe like this. And then we go to an angle of pi over 3, and there we have r is equal to 2. So pi over 3 and r is equal to 2, so that gives us a point here. Pi over 2, so that would be this 90-degree angle, and then in that case, r is equal to 0, so that means that we have a point here. And by the way, anytime r is 0, no matter what the angle is, you're still going to get a point at the origin, right? It doesn't really matter what the angle is. If r is 0, it just forces that point to be at the origin. Okay, so when theta is 2 pi over 3, so 2 pi over 3 is here, is this angle here. Maybe I'll start, because some of these angles are now going to be a little trickier, so I'll start drawing them. So when theta is 2 pi over 3, r is supposed to be equal to -2. And so that means that we're going to go on this angle, but in the opposite direction, and put a point at 2 in the opposite direction. Okay, so next up we have 3 pi over 4 and approximately -2.83. So 3 pi over 4, that would be this angle, but we have a negative r value, so that means we want to go this way when we actually put our point down. And so we want to go to a radius of approximately -0.2 or -2.38. Or sorry, I keep saying things backwards, 2.83. So that would be, again, pretty close to -3, so somewhere maybe like around here. And then just a couple points left. So next point is we go to 5 pi over 6 as our angle. So 5 pi over 6 would be this angle. And then we're going in the negative direction, so that means that we're actually going to be going along this direction here. And so we're supposed to go to -3.46. So again, that's about halfway between 3 and 4. So maybe somewhere like here. And then the last point that we have is at pi, we're supposed to be at -4. So if we go to an angle of pi, that would be here. But -4 means we go in the opposite direction. And so that point we already have. And so that's one thing about polar equations that's different from rectangular equations, is that you get a lot of repeated values. So notice I only went from 0 to pi here. If I had gone from 0 to 2 pi, it would still look the same. It would just be, we would just kind of keep repeating values. So what does this look like? Well, it shouldn't be too surprising based on the equation we came up with the other day, that it should be a circle with a center of 2, 0, right? That's the center of the circle, and a radius of 2. And so that agrees with the equation that we came up with last time. So I think that's kind of cool that it works out that way. So the next example we're going to do is we're going to sketch the graph of r is equal to sine of 2 times theta. So we'll see that when we go through this, we're not actually going to graph the entire shape. So in this case, so on the last example we did, it was enough to just go from 0 to pi. It really kind of varies based on what the shape of the graph looks like. For this specific graph, 0 to pi is not going to give us the full shape, but I just think it's kind of boring to just plot a gajillion points. So I want to do some of them, and then we'll go to Desmos and use that to kind of see what the rest of the shape of the graph looks like. Okay, so how does this work? Well, we're plugging in this angle theta, but when we go to evaluate sine of the angle, we're actually doing 2 times the angle. So for example, for the first part, we're doing r is equal to sine of 2 times 0. And so in this case, it doesn't really make a difference because 2 times 0 is 0. So we just have sine of 0, and that is equal to 0. But in this next one, it will make a difference. So we're going to be doing sine of 2 times pi over 6. And sine of 2 times pi over 6, well, that's the same thing as sine of pi over 3. And so what is sine of pi over 3? Well, that would be square root of 3 over 2, right? If you go on the unit circle to an angle of pi over 3, the y coordinate would be square root of 3 over 2. And let's actually get a decimal estimate for that. So square root of 3 over 2, sorry, I forgot to do this ahead of time, and I forget what it's equal to. So it's approximately 0.87. So I'm going to just erase this so we can make space for that. But yeah, I would definitely encourage you to pause the video and work some of these out yourself. So maybe we'll do like one more together, and then I'll just kind of fill out the rest of the table because I just don't think it's the most interesting thing to watch. So how would we find this third value? Now we would be doing sine of 2 times pi over 4. And what is 2 times pi over 4? Well, that would be pi over 2. And so what is sine of pi over 2? That would be equal to 1. So the one thing that I think makes this a little tricky, and we'll see this when we go to actually graph it, is that when we go to graph these, we're using the angles that are listed on the table. It's just that when we're taking sine, when we're actually kind of plugging into the equation, that's where we're going to be doing 2 times the angle. So I just want to kind of make that distinction. Okay, so for the next one, we have sine of 2 times pi over 3. So 2 pi over 3 is going to give us, again, actually the same value, right? That's going to be square root of 3 over 2. The next point, we're doing 2 times pi over 2, so that's pi. So that's going to give us sine of pi, which is 0. The next one is 2 pi over 3, and I feel like okay, never mind. Thought maybe I skipped something, but I think we're okay. So 2 pi over 3, that would be sine of 4 pi over 3. And so sine of 4 pi over 3 is going to be negative square root of 3 over 2. And that's approximately negative 0.87. And then 3 pi over 4, if we multiply that by 2, that is 3 pi over 2. And so sine of 3 pi over 2 is negative 1. And then if we go to 5 pi over 6, so 2 times 5 pi over 6 is 5 pi over 3. And sine of 5 pi over 3 is going to be, again, negative square root of 3 over 2. So that's approximately negative 0.87. And then finally, pi, if we do sine of 2 times pi, that's sine of 2 pi, and that's going to be equal to 0. So just plugging the points basically into this equation, just like you do actually, if you're graphing like y is equal to sine of 2x, right? It's the same idea, just plugging in numbers for a theta. Okay, so let's go and graph these now. So we can now completely forget about this sine of 2 theta business, forget about the 2 theta, and now we're literally just plotting these points the same way that we did in Wednesday's video. So 0, 0, we know how to graph that, right? That's angle of 0, radius is 0, but like we said, anytime the radius is 0, it's going to be at the origin. Okay, so next we're going to an angle of pi over 6. and we're going to an R value of approximately 0.87. So that's going to be somewhere like this. So next we're going to an angle of pi over 4. And at pi over 4, we have an R value of 1. So that's going to be here. Next, we're going to pi over 3. So we're going to an angle of pi over 3, and our R value is 0.87 again. So that's like this. And then at pi over 2, we're back to 0. So if you connect the dots here, it kind of makes this like petal shape like this. And I probably should have made this, this grid a little bit bigger, but we'll be able to see this graph more nicely in a moment. So we just finished this one, right? Pi over 2 and 0. And so now we're going to an angle of 2 pi over 3. So now we're getting into negative radii. So I'll help us visualize this by doing this. So here's 2 pi over 3. And our radius in this case is negative 0.87. And so that means that we want to go in the opposite direction along this yellow line. So that means that instead our angle is going to be in this direction. And we're going to have R equal to negative 0.87. So that's going to be somewhere like around here. Okay. And then our next point is at 3 pi over 4. So that's here. But again, we have a negative R value. And so we want to go about a distance of 1 in this negative direction. And so that puts our point here. And then our next point has 5 pi over 6 as the angle. So that's here. Oops. So 5 pi over 6 is like this. But we want to go in the negative direction. So we're going to be going along this line. And again, we have an R value of about negative 0.87. So that's going to put our point somewhere here. And so if you kind of think of of how we've been traveling, again, we're kind of making this other petal of this shape. So we came now like this. And I just made that a little bit bigger than it should be. Let me just try to fix that. So if you were to continue with this, so we didn't, we just did from 0 to pi. If you were to go from 0 to 2 pi, what you would see is that you would end up with, and hopefully I won't butcher this too much, but you'll end up with another petal like that, and then another petal like that. And I did not do a good job on that. But basically what we saw on the right-hand side, you would see the exact same thing. So I want to pull this up on Desmos, and then we'll look at some other examples. So here is the actual graph of sine of 2 theta. And let me make this a little easier to see. And so also, by the way, this was the one we did earlier, right? We did 4 times cosine of theta, and that gives you a circle with radius 2 centered at the point 2, 0. So I just want to quickly show you the difference between sine of 2 theta, and then if you had done cosine of 2 theta instead, that would give you this graph in blue. So if you think about it, it kind of makes sense because the graphs of sine and cosine, they go through the same values, but they're just kind of at different angles. And so basically what's happening with cosine is that you're getting those same R values, you're just getting them at different angles. And so it's the same shape, but kind of twisted. So another interesting thing is if you take so right now it's sine of 2 theta. If we change what that number is, that's going to change our graph. So if you just make it sine of theta, then that actually just gives you a circle. And that's actually similar to what we did here, right? So 4 times cosine of theta. So if we make this one just cosine of theta, that will give us also a circle. So that's not super interesting. But what is interesting is if I change this, so that was 2. If I change this to being 3 or 4 or 5, or 6, you can see that there's something kind of interesting going on with the petals. So basically, if the number here is an even number, then we get twice as many petals as that number. But if the number is an odd number, then you actually get the same number of petals as the number. So I'm sure there's some pre-calculus classes where you really delve into this. We just don't really have time to spend much time getting really into this, but I just kind of wanted to show you. And then same thing with cosine. If you do cosine of 3 theta versus 4 theta versus, 5 5 theta versus 6 theta. So kind of interesting how that works out. And if you're curious, I would recommend, make a table and graph these yourself, and you'll see kind of where these shapes come from. So now I just wanted to show you a few other examples that I think are particularly kind of cool graphs. So this one is r is equal to 2 plus 2 sine of theta. So this is what's called a cardioid. So I wouldn't say, I'm not really showing you this one because I think it's that cool. We'll see there's some later that I think are a lot more like elaborate. But this is kind of a famous one. So cardioids are these kind of like, I think they're called that because it's vaguely heart-shaped. And I think if you kind of play around with these numbers, you can change what the exact details are of the shape. And that goes with for like all of these different equations we're looking at. I think it's actually pretty fun to kind of go through and just like play around with what you can change in them and see how that changes the shape. So next one is sine of theta over 2. That gives you a shape like this. So next one is theta times sine of 2 theta, or actually let's make this sine of theta first. So this is theta times sine of theta. And this one's kind of interesting because it actually gets bigger and bigger the more kind of values you go through. So most of the graphs we've been looking at are just angles between 0 and 2 pi, and most of them start to repeat themselves. But this one doesn't. So if right now this is going from 0 to 12 pi, if I were to make this 14 pi, it gets bigger, 16 pi, etc. So this one, basically because you're multiplying theta with sine of theta, it kind of gives you these bigger and bigger and bigger circles as you plug in more. And then I typed in earlier, if you change this to like sine of 2 theta, all of a sudden that gives you something totally different, right? Or sine of 3 theta. So there's a lot of really cool graphs that you can get out of kind of experimenting with these. I think this was the one that I especially really like. So this is 1 over square root of theta. So it gives you this kind of like coil shape. That's pretty cool. And then last one I have queued up here is sine of theta plus sine of 5 theta over 2 cubed. And that gives this cool kind of like floral thing. But like I said, if you just kind of play around with, changing different things in this equation. So maybe if I make this just like 5 pi instead of 5 pi over 2, I get something totally different. If I change this to 4 theta, there's just a lot of different things that you can kind of play around with to see how they affect the graph. So I think it's personally an interesting thing to do, to just kind of like type in some random equation and relating r and theta in different ways and kind of see what shape that ends up giving you. So last thing I just wanted to say in this video is that there's one question on the homework that is a multiple choice graphing question. So if you're just not really interested in this stuff, you're welcome to just kind of graph each of these on Desmos and use that to figure out which graph is which. I wouldn't hold it against you if you do it like that. But you can also do basically what we did earlier with making a table. And it's a little trickier to maybe see here because they're putting them on rectangular grids instead of polar grids. But if you go through and make a table and go from 0 to 2 pi is usually a good bet, you should be able to kind of figure out from your shape that you drew which graph it matches with, or at least maybe start drawing the graph. And I think even just by starting to draw the graph, you can probably figure out which graph it's going to be, even without like getting the whole picture. So that is it for today.